Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we're starting the talk more promptly than most theory talks because we just have the room for an hour, and we don't want to miss a word of our wonderful speaker's talk. So Tsinghua Teng is visiting from BU for a total of almost 2 months. You're here still for another month, or
6 weeks, yeah.
He's here for another 6 weeks. So if you want to talk to him, he's here for a while, and he will be talking about paths beyond local search on the randomized query complexity of fixed-point computation.
Yeah, thanks, Jennifer. So over the last decade, computational game theory has become increasingly active in computer science. As a result, the fixed point concept and its, the close cousin, Nash equilibrium, has gained popularity and importance within computer science. And in this talk, I would like to discuss a recent result on the computation of fixed point. And I will try to express some of my excitement over this result, but also would like to express still my puzzledness over the overall picture concerning about fixed point computation. So this is a joint work with Chen from Tsinghua, and he will go to Princeton as a postdoc next semester. So about 100 years ago, Brouwer made a very simple discovery. That is, every continuous map from a three-dimensional simplex, or tetrahedron, to itself must have a fixed point. So that is a point that satisfies fx equal to x, where x is the mapping. And soon his theorem was extended to arbitrary dimensions and to arbitrary convex sets, and also become one of the most fundamental theorems in mathematics. So the Brouwer's fixed point theorem has many applications, both mathematically and also in applied science. For example, it guarantees that every time you look at a map, reasonably drawn map, there must be a point called you are here, because it's a fixed point. Okay, and as long as the map is continuous of our universe to that map, okay, then there must be a fixed point. So in more applied domain, for example, in 1950s, Nash used Brouwer's fixed point theorem and some of its extensions to establish the equilibrium point for a non-cooperative game. And I wrote the Brouwer a few years later, extended to market equilibrium. So even though the proof technique is very powerful, it allows us to establish the existence of a solution that satisfies certain balancing conditions. However, the proof is in some sense highly non-constructive, and also in the sense that in modern days of view, we talk about polynomial computability, and it's even lesser constructive. Okay, so for some maps, such as the contractive maps, namely a map that satisfy the following condition with a Lipschitz constant less than 1, then one can use numerical techniques to find a very good approximate fixed point. Okay, so essentially you can just apply certain iterations to it will converge. But for general conditions, the continuous maps, including the map built for Nash equilibrium, there are few techniques and methods or heuristics that have been developed and promoted over the years. The famous one is by Scarf. However, none of those was shown to be in polynomial time. Right? So they are kind of far away from being polynomial time. So that's essentially the state of knowledge we have over the last 50 years. Okay?
But doesn't matters require you to do derivatives?
Yeah, there's certain things that involve how the function is given to you. Okay?
In the contractive case, it's polynomial time algorithms?
Depends on how you define it. Depends how you define it. Yeah. But it's much easier case. It's a much easier case. Okay. So you can see that a lot of confusion also in our discussion is that within computer science or theoretical computer science, we are very much influenced by the classical Turing model, in which things have finite descriptions, and the fixed point is inherently continuous. Right? It's inherent, by definition, it's inherently continuous. So it's a little bit hard sometimes for us to really room in to say what is precise complexity, including the contractive case. Right? So fortunately, there are few great establishment along the way build the combinatorial connections between fixed point in the Brouwer sense to fixed point more closer to our language, more discrete mathematics. Okay, so in fact, for example, Scarf's method for computing approximate fixed point is very much closely built upon an observation of Sperner.
What is legal?
So I will define. Yeah. So here is a very simple lemma which proved that about 10 years after Brouwer's fixed point theorem, a beautiful lemma called Sperner's lemma. It states as following: that imagine you have a sort of a triangulation of a triangle domain in 2 dimensions, where one corner colored red, one green, and one blue, and the side of the red-blue edges are colored only with red-blue, and the red-green edges only colored by red and green, and so on. And you can color anywhere interiorly, any colors of the 3. So then Sperner's lemma guarantees that once you flood in the color, there must be a base triangle that has all 3 colors. And this, you can view this as a sort of discrete version of fixed point. So in some sense, from continuous fixed point function, you can build the color assignment, and in some sense, if you have a 3-colored triangle, there will be a fixed point close by. It didn't say inside it, but there's a fixed point close by. So that's essentially, for example, Scarf is keep on dividing the domain and give you a point increasingly closer to perceived fixed points. Okay? So this actually is very simple combinatorial lemma. Actually, in 1 dimension is even simpler. That is, imagine you have an interval with, 1 point colored red, 1 colored blue, and all the internally color any way you like. Then clearly there must be 1 interval has 2 colors. Right? That's the notion of continuity, and this basically is the 2-dimensional version of that. And it can be extended to high dimension. Right? So this, but one thing nice is very combinatorial, right? You can think about we don't have to talk about epsilon and all those things anymore.
So is there somewhere in this argumentation hidden the pigeonhole principle or the axiom?
It's actually using the parity argument. So Sperner proved that the number of such triangle must be odd, since 0 is an even number, and hence there must be 1. So that's how it's argued. And there's other quasi-constructive one. I will give you an indication along the way. So there's other variations of such discrete fixed point theorems. For example, if your domain, convex domain, is a grid, is a square, then potentially one of the way to decompose your domain is using regular grid. And you can define fixed point theorems or problems on such a domain. And this problem played a very important role in the recent development of the complexity of Nash equilibrium. Okay, so here is another discrete fixed point problem. That is, I gave you a regular grid, and you color one side with red, one side with green, and the other 2 sides with blue. So 3 colors, and you can color inside anywhere you like, any color you like. Okay, so then we guarantee that there must be a square actually, or you can also decompose a square into triangles that has all 3 colors, right? So this panchromatic elements is also true here. Okay, so again, this can be proved either using parity argument or this kind of a constructive way called path following, right? So one way to find such a triangle is that because if you look at this side, there must be a transition from red to green at the very beginning. So then you follow a path, keeping red to your left, and keep green to your right, and stop when you find the third color. And this one will keep on going, and so basically the green is always on your right. It has to start somewhere in the middle with all three colors. It cannot come out anymore. Okay, so this is what we call path following. So, but if you think about it, path following is a very important method for mathematical programming, right? The simplex method is path following. It follows paths on the polytope. The interior point method is path following. It basically follow path interior of the polytope. And so this is a very generic approach for mathematical programming called path following. Okay, so this thing can be also extended to higher dimension. For example, if you have a d-dimensional grid, and you can use d+1 colors, and again you use a very similar boundary condition, then it will guarantee you to have a cube that has all colors, and you can decompose the cube into simplex, and you can have the simplex version. Okay. So
what is any boundary condition?
No, it's a condition similar to what I described. You have three d+1 colors. You use on the principal facets. All other facets you color with the d+1 colors. Okay. So this is a discrete version. So in a grid development, Papa Dimitriou used this to define a family of search problem or complexity class, what he called PPAD. So what is PPAD? PPAD is really a version of thinking about Sperner lemma, but you think large and think exponentially. Right. So here is sort of a functional version of PPAD, or a concrete example of a PPAD problem. That is, my input is this virtual input of a triangular domain. It's not explicitly given to you. It's a virtual input. So this is our domain. And the real input is basically a circuit of polynomial size. Right. So polynomial in the log of the whatever the bits you need to express this, and so this circuit has basically the circuit take essentially 2n input, give you the coordinates in the system, and output a color, one of the three, and your job is basically take this circuit, and also this circuit satisfies, like for example, boundary condition. So let's ignore this boundary issue right now. And your job is to find a trichromatic simplex in the landscape. Okay, so this is a problem of PPAD. And actually, this particular version was shown to be complete for the family only recently by one of my collaborators, Chen and Xiaotie. So I think last year they proved the 2D case. But in higher dimensional case, from 90s, Crystal know all those things are PPAD complete. So then you clearly will think, how hard is it indeed to find such a triangle, right? So if you look at the computer science, at the early stage, beyond sorting and some graph algorithm, most of the time we are solving optimizations. So we have some kind of objective function that we want to optimize, either minimize or maximize. But those type of conditions are very different from maximization, right? So the parity is somehow different from optimization. So here is the tale of in some sense, some contrasting development between the problems related with fixed points and problems related with optimization. I'm just giving you a few examples, and maybe more, and Mihalis probably can give you a list of thousand of contrasts. So for example, in local search, we want to find local optimal. And if you look at linear programming, it's a local search problem. It just happened to be the local optimal is global optimal. And that after, few decades of struggle, we know now it's in P, weakly P. And, but if you look at its cousin, namely two-player game zero sum to a general two-player game, Nash equilibrium, that is still unknown. Right. So after 50 years struggle, we still don't know whether it's in P or not. And if you look at some other similar method developed for local search and say Nash equilibrium, like the simplex method of Danzig, or Lemke-Hausen method for fixed point or for equilibrium. Then, for example, in the smooth model, if you perturb the linear program for this local optimization, now we know it's in smooth P. When you perturb it, the worst case quickly dropped. But in Lemke-Hausen case, one can prove if actually it's in P, then the original problem is already in randomized RP. Right? So there's a strong indication that it may not be true anymore, like perturbation won't help. And if you look at the family of the complexity class defined based on local search, polynomial local search, and all the PPAD I just mentioned. For example, local search under certain limited condition, one can develop fairly general fully polynomial time approximation scheme. So let's ignore the technicality of the definition of approximation right now. But for some reasonable notion, we can compute approximate local optimal in fully polynomial time. But again, for example, in Nash equilibrium, if it has a fully polynomial time approximation scheme, then again Nash will just in P by itself. So the approximation also here didn't quite help you. And so one thing I would like to focus a little bit more on today's talk is that for certain case, Aldous in 80s showed that randomization actually helped to speed up local search. And it has been open for a very long time that whether somehow randomization will help fixed point computation. So that will be the focus I will have today. Okay.
In which sense did Aldous prove that randomization helps? I mean, is it known to be hard if you don't use randomness?
Yeah, I will show you the gap. You can put decisive gap under certain models. That's what I'm going to discuss. So in some sense, one of the motivation question for me, which I don't know the answer still today, is fixed point computation fundamentally harder than local search, or is just because we don't teach a fixed point, like in my generation, we didn't really learn much about fixed point, then we certainly don't know what to do with them, right? So I'm looking for some fundamental reason, maybe to show that the fixed point computation is non-trivial. Okay. So the model I would like to consider in this talk is a black box query model. So let me just give an impression of black box query model in the fixed point computation here. So imagine we take this grid version of a discrete fixed point problem. For Brouwer's function, you can build approximation like a scarf. So if you have such a result, you can have implication of how quickly you can compute approximate fixed point in scarf sense. Okay. So in such model, we have this the grid, and if I give you a query point, there's a black box that will tell you what's color. So in some sense, I take a PPAD model of crystal and just hide this polynomial time coloring circuit as an oracle, and you just ask me a question, what's the color of it? So that's the model. And if you want to know what's the color of this, I give you the color. And I'm interested to know how many queries you have to ask so that you can find a 3-colored simplex, for example, or panchromatic simplex in D dimension. So that's the model. So it could be 2 dimensions, 3 dimensions. So I'm basically giving you ability to query a particular point and get the color back. And your job is to find a panchromatic simplex inside the embedding. Okay. So we can define 2 complexities. One is the deterministic complexity, for example, in D dimension. Suppose my grid is n by n by n by n in D dimension. And so let me define the deterministic query complexity for this problem with primary dimension D and size n to be this symbol. Okay. And I can also define so-called randomized query complexity. Right? Namely, your algorithm can do randomizations. Right? In addition to move deterministically, you have chance to sample. You have chance to flip coins. Okay? So in some sense, I would like to study their discrepancy. here. That's one of the parameters I would like to study. So here is a previous result. So this is actually a beautiful model first proposed in 1989 by Hirsch, Papadimitriou, and Wawasas. I think also part of Wawasas' thesis, potentially, perhaps. Right? So it's Wawasas' thesis from Stanford, 1989. So they proved that in the deterministic case, in this model, the fixed point complexity is has to be more than n to the power d minus 2. So they argue that here is a lower bound for fixed point computation if you want to do deterministically. And a few years ago in a Fox paper, Chen and Xiaotie then tighten this bound. They actually finally get rid of one of the one. They have a slightly new way of arguing for parity, and that allowed them to achieve an optimal bound. So if you want to do deterministically, you have to pay basically n to the power d minus 1. So what is n to the power d minus 1? If you really think about it, it's really, if you cut the cube into half, the surface size of the cut is n to the power d minus 1. So in some sense, one way to achieve the upper bound is to do divide and conquer. Namely, you cut the grid into half, you check the parity. In 2 dimensions, you can talk about, I have paths going how many times to the other side. And if I start here, then if I go even time, I know fixed point is here, otherwise it's on the other side. But in higher dimension, you have to have slightly different notion of winding numbers. And nevertheless, they can do locally. They show that both upper and lower case you can achieve this, and it's also lower bound. Right. So in some sense here, I mentioned 2 basic techniques to solve fixed points. One is based on this divide and conquer. You cut the domain into half. You somehow check the parity along the boundary, then decide where to drop. And the other technique is this path following. Right? You follow a path, and the path tell you this direction, you go this direction. The path say turn, you turn. And somehow you knew once you couldn't move anymore, that's fixed point. Right? So that's this 2 approach to find. Then clearly, the complexity of divide and conquer is the surface volume area you have to pay, and the path following complexity is bounded by how long is the path. If you blindly follow a long path, you have to keep on walking, like the simplex method, for example. Okay, so clearly here one of the questions left open in both papers is what is randomized complexity here? So that's open from both papers.
Remove logarithmic factors.
Pardon me?
In the theta, you remove logarithmic factors. Or
you mean here? I think there's no logarithmic factors.
No.
But for this binary search, you don't need
No, because you divide and conquer, you have a geometric decay size, right? So only the first cut matters, right? Okay. I mean, it's geometric decay, right? Binary search, right? So you only pay for the first cut. All other cuts are smaller, right? Right, good. So what is the optimization parallel to this? Is an oracle model for local search. Right. So here is a black box model for local search. That is, I gave you, for example, similar like a grid situation. And I have a function which maps from the grid point to integers or real numbers, doesn't matter. Let's just say integers. And then my function is given to you as an oracle. Namely, everywhere you ask, I open a card for you, say 100, 1,000,000, 2, -1. So you have to ask me a question to answer this. And so again, you can define the deterministic complexity for local search. And you can also argue, essentially, using very similar technique like the fixed point, you can argue deterministically the complexity is also n to the power d minus 1. So somehow the divide and conquer is also the way to go, and is optimal for local search. Okay, so that's a deterministic case. So deterministically, there's no separation between these 2 problems in this oracle model. Both can be solved by divide and conquer. And both also can be solved by path following. Right? Because local search, you can do path following. The steep descent is path following method. Right? So in 1983, Aldous made a beautiful argument, very simple, to show actually the randomized complexity of this problem is n to the power d over 2. So clearly this is decisive gap now. The randomization helped me in this case because there's a lower bound over here, right? So here is all those arguments, and it's such a nice thing. If you don't want to do precisely, you can say in 2 minutes. Okay, if you want to do precisely, that's a separate story. So it's a very simple algorithm. You say, let's randomly query n to the power d over 2 point uniformly at random. You go to your grid, you randomly query certain points. Then you pay that much number of queries. Then you take the minimum of the things you discovered. You take the minimum of things you discovered. Then you do path following. You just go down a steep descent path, and the end of the path will be your answer, right? So this is like the one round simulated annealing, right? So in one side you do it's just a one step simulated annealing, right? You fix your temperature after your query. That's all you do. So this complexity essentially is the number of query you already paid for sampling, and clearly the length of path you travel. But you can easily argue the expected length of path you travel is also no more than n to the power d over 2. So why is that? Because if you imagine you have to travel a really long path, then the sample will intersect it. Right? If you have really long path, if you sample, the sample will have intersection. Since you start at the last segment of the path, and the last segment are free of sample, and it cannot be too long. Right? If the last segment is too long, the sample will hit it with decent probability, and hence the expectation of with high probability is this. Right? So it's a beautiful argument. Okay. So then, an obvious question clearly, those eventually, the bound is eventually shown to be tight or approximately tight by sequence of work by Scott Aronson. I think I misspelled his name, right? There must be 2 R's, right? Aronson. Oh, I spelled correctly. Okay. So I will check. So, but Scott, when he was studying the quantum complexity of local search, and he got a bound which is not tight, and eventually was tightened by Shen Zhang from Princeton, and lower dimension by Xiaoming Sun and Andy Yao last Fox. So they get a tighter bound, but also related with quantum complexity. So clearly, a central question here we are considering is, can randomization help fixed point computation? Right. So our intuition says no, right? In some sense, this really shows fixed point computation is very different from local search. And so here is a few structural differences that I can enumerate. So one of the main difference, at least in our and probably many people, most of you's mind, is this notion of measure of progress, right? So if you really think about path following in local search landscape, so basically I go down a local chain like a simplex method, right? I'm improving my objective, and as space goes on, you're happier because there's a decisive number. You say I'm improving, right? So there's a decisive number to tell you keep on going, you're doing well. And when you do path following in fixed point computation, you have to have a lot of faith, right? Because really, there's nothing else to tell you. All it tells you is just go here, eventually you will find it. It's much more blind. And there's not much sort of a notion of how much progress, how much remains to happen. You just knew when you go down the chain, you will find a fixed point. Right? So clearly there's some kind of difference, maybe psychological. I want to turn it into complexity, right? So it could be, but this is one of the one. But for example, when you sample 2 points here, and you say, where would you like to do a steep descent? Statistically, you will say go here, right? Because you think this is clearly better bet. You feel happier to bet here. But if I sample 2 triangles for you in this sea of coloring, then you say, I gave you 2 colors like this. I said, where do you start? They look the same. Which one you choose? Close to the blue one. That's the other way to choose, but it didn't always work that way. So
Well, they are equally close.
equally in this particular case. Good try.
In the local search, you wanted to find the minimum, yeah?
Yeah, local minimum. Local minimum. Good. Okay. So this, I think, is probably fundamental because one, clearly you have some information moving around, and the other is a more structural difference. If you follow a locally decreasing path, suppose you want to do minimization, then clearly this path will not self-intersect. Right? It's a cyclic. Right? You cannot have self-intersection because it's monotonically decreasing path. But if you follow, this left-hand rule of coloring, you can loop around. So this can be different. There's another structural difference. Okay. So clearly the question is whether those differences makes complexity implication, and we are finally able to argue that randomization does not help fixed point computation, and we show that it actually has a lower bound also n to the power d minus 1. So basically, with or without sample, ability to sample, you are paying about the same, right?
What is the lower bound of randomness for local search?
It's n to the power d over 2.
That's also lower bound.
Yeah, there's maybe a log there. I forgot it there now. Yeah. Right. Okay. So there is all tight in the n to the power d over 2 range. Yeah. So the interesting part, I think, is also the significant gap between these two problems is only revealed by randomized model here. The deterministic model they're really like the same problem, right? So somehow randomization revealed the discrepancy here. Okay. So it has the following implication, that is, in this randomized query model, for example, global optimization is clearly harder than fixed point, because there you can easily prove a lower bound has to be n to the power d. You have to really look everywhere, roughly speaking, if you want to find the globally optimal. And the fixed point computation is decisively harder in this randomized query model than local search. So in the rest of time, I will give you an impression of the proof, and I will try to hide some of the tedious steps, and at least give you an impression how statistically we can, how we argue this randomized lower bound.
The paper here?
So we put in an archive and we send to Fox right now, right? So.
Does the lower bound also hold postponements lemma?
Pardon me?
Does the lower bound also?
Yeah. You can, once you can convert, this will be all converted to the high dimension Sperner lemma. So the conversion actually is very challenging. But it often appears, it's very tedious, right? You have to make sure all the colors are right? So it's like engineering work. So I will show you a few partial examples here, right? So I will introduce 3 search problems as an intermediate step, and increasingly simpler for us to reason, because the fixed point is slightly hard to reason. I guess in part because if you think about the coloring, we lose a little bit of orientation of the situation. So we follow the lead of Crystal, try to get more and more into graph theory, but then actually we deviate from Crystal. We leave graph theory completely and go to a string problem, which I think is a problem involving strings. So we have 3 problems. One is I will define later, so don't worry about what they look like now. So first we basically almost reduce to a PPAD version of this, so that I can, from the if I give you a PPAD instance, I need to build an instance of coloring for you, right? So this way, if I get the lower bound here, I get the coloring side. So I need to reverse the engineering what Crystal did. He normally goes this direction. So for lower bound, we have to go to the other direction. Okay, and then we will relax the PPAD condition a little bit. But PPAD condition basically say you have a field node of degree 1 in degree 1 and odd degree 1, and the field node which has only in degree without odd degree, and vice versa. So you can have this starting vortex and sink vortex. And here basically we will relax a little bit to allow self-intersections. As long as most of vortex satisfies this Euler condition, the number in degree is equal to the number odd degree. And the sink and source are defined by the discrepancy. Okay, so this is a simple step. And I think an interesting step, which I will define as string. So ultimately, we convert into a string problem. So involving a string of alphabet, I will define a query model so that the name of the game is that I tell you the beginning of the string, the name, and you can query and you can get more and more information. And your job is to find who is the end of the string, what's the last few letters. So I will define this more formally. And somehow this model is much easier to argue for randomized complexity. So essentially, eventually, from string, I will build this model. From this model, I will build this. From this, I will build coloring. And therefore, by giving a lower bound here, so this is basically the step, right? From string, we have to reverse engineering to build all the way to coloring. And then we set a lower bound for this. And this lower bound will go through. So that's the outline of the proof. Okay. So let me just start something slightly simpler related with coloring, and it can be a little bit tedious too. Then we can focus on the string, which I find is a very interesting part. Okay. So what is PPAD graph? So here is crystal defined. A PPAD graph is a graph, directed graph, where the in degree and out degree of every vertex is no more than 1. That can be 0. And you always have a starting vertex has in degree 0. So you always know where to start, which means you always know there's a fixed point. And this implies clearly there must be a fixed point which has no out degree, right? And the job of PPAD graph intuitively is to try to find the fixed point. Okay. So we'll focus on an even simpler case of PPAD graph. So in our construction, we'll hide one long path. Remember that you have to build an instance to defeat both local path following and divide and conquer. Right? So that's basically the name of the game, right? You somehow need to hide a path in this grid. Somehow this path has to be long, because otherwise you just follow the path. So this has to be long enough, and then when you do divide and conquer, you couldn't discover it. So that's basically the sort of the complexity of the construction. And so we'll stay with one path set, namely our graph eventually created just a single path with a lot of cycles. But this path is long. Okay. So here is a query model. Query model is that your input is this sort of landscape of a grid. And I'm giving you a starting vertex, so that's given to you. And your oracle, you can ask whether a particular edge is in or out. So that's query model. Or you can convert it into, I can ask vertex where I'm pointing to. That's equivalent. You can simulate it that way. Okay. So the simplistic way to think is just, you can only ask queries. Do you have this edge or not? Going in that particular direction. Okay. So that's a model. And so the complexity clearly is how many queries you have to ask. Eventually you know the fixed point. Okay, so that's the first step. And let me just mention the result and just show you the picture without going through the step now. So essentially, not surprisingly, just follow the intuition of crystal, that PPAD can be reduced to fixed point in the reverse direction. Okay, which he also did. And so I just gave you, this basically implies that if you have a lower bound on the graph, then you have a lower bound on the coloring, right? So the correct direction. And here is basically a impression of the reduction. So if I give you a PPAD graph, then you have to build a coloring. And this coloring somehow has to realize the following thing. If you go to end of the path, you have to go to a trichromatic simplex. Right. So you have engineering out this thing, which can be built. Okay, so I give you this collection. You can actually eventually expand it out into coloring, like Sperner's lemma. Okay, in any version of discrete fixed point, this can be converted. Once you get the one, you can get the rest. Okay, so that's the first step. So hence, you know, if you somehow allow you to query here, you can get a fixed point. There's a few technical detail, namely you have to get the query lined up. When you ask query here, you have to show in the other model you only ask constant number of queries. Right? So there's some technical detail you need to go. Okay. So then basically we'll try to relax our condition a little bit and to allow our path to be self-disjoint. This is the simplest step. And not surprisingly, this can go to the PPAD graph. If I give you this, and basically I will somehow try to realize the PPAD graph. In 2 dimensions, it's actually kind of in 3 dimensions, you can somehow avoid each other. Because 3D, you can shoot over. In 2D, it's a planar case. You can't shoot over. So you have to use so I give you the impression to build. The query is same thing. The query is same thing. So here is roughly the building. If I give you a self-binding thing, you build multiple blocks, and they simulate the whatever the entrance here. And so locally, you have to define very carefully how they cross. Okay, you have to define very carefully how they cross. So I'm not going to bore you with all the steps now. But the impression is this. With this, you can define, so the self-binding one, you can actually say, if you have self-binding paths, you will be able to pull out a path with collection of cycles. Because in 2 dimensions, it's important to have cycles. Because the planarity, you can't self-avoid this. But in 3 dimensions, you can literally go from path to path. Because you give you a little bit more space, you can shoot over anywhere. Right? So that's why most of the old PPAD complete problem on fixed point are all done in 3D because of this. In 2D, one needs a technique like this to go through. Okay? So when you have the end, you have the end there. So those are fairly mechanical steps. Okay? So the most important part is how we somehow envision a path in this grid that's long and hard to find, either by path following or by divide and conquer. So that's the basic step. So
why was the case that it should be long and not short?
Because if it's short, you can just do, because I gave you a starting vertex already. You can just path follow. You just say, who is my next step? So that's only, so which means you have to build a path at least of length n to the power d minus 1. So that's why, for example, in local search, when you do lower bound, like Scott Arison case, they are hiding a much shorter path. Right, because they're achieving a lower bound of n to the power d over 2, so their path only needs that length. But here, basically, you have to involve most of the vertex, and then still you say it's hidden. You can't discover it. So I think that's the structural difference here. Yeah, but of course, the query you ask here is a little bit weaker, because you don't know a value here.
Why do you know the starting point?
Pardon me?
Why do you know the starting point?
Oh, that's how PPAD, for example, is defined. Or Sperner lemma, you know its starting point. You can enter from the you have a starting point. Yeah. So that's why you have to. I have to give you one. Because otherwise, I can trick you. You will cycle around, right? You start from a place, you just cycle around. So then you have to discover all the cycles. Right? So I give you easy task now. I give you a starting point. Okay. So there's a second step. I don't want to spend too much time in this technical part. So that basically means that once you can build a winding path, self-intersecting is okay, the lower bound will carry through. Okay, the lower bound will carry through. So here is a string problem that we introduced. Somehow it's easier for this sort of recurrence analysis of probability. And so it's a string, what we call a D non-repeating string. So essentially I have an alphabet, and I will give you, let's say alphabet is 1 to n, and I will build a string of certain length. Okay, certain length. And it's D non-repeating, it means every string of length d will appear at most once. So that's the main condition. So like 2 non-repeating, every pair of numbers appear at most once. And D non-repeating is every sequence of D numbers appear no more than once. Okay. There's some other technicality, namely, but those are all minor technicality, just for the simplicity of argument. Namely, if the index is a multiple of D, we're using an odd number, otherwise we use an even number. index a multiple of D, we use odd number, otherwise we use even. Those are for technicality. It's not profoundly important. But profoundly important is I promise you a string that is non-repeating. Okay. So somehow I will build a random set of such a string and eventually use them to define paths and then coloring. So that's basically the technique, right? So somehow you envision a path and then you color like a Sperner lemma. Okay. So for example, here is an example of two non-repeating string. So at every odd slot we have odd even number, and other set we have odd number, and you can easily check. I promise you, there's no two numbers appear twice here in this string. Okay, in consecutive row. Okay. So this is called head of a string. So you can see this, like I will give you coordinates. Essentially, I give you coordinates of the path, right? And this will be the end of tail of string. Okay. So what is the query model you can do? So here is query model you can ask. The job is to find the tail. I give you the head. Okay. So this is like single pass, you know. And I can ask you to ask the following queries. You're asking query for a name of D numbers, and you ask, is this number inside or not? That's one information you want to know. The second information you want to know is who is the number before me and who is the number after me. So those are the only information we are given to you. Okay. So for example, if you ask 8-5, the answer will be no. So there's nothing before you, nothing after you, which means you're not there. Okay. So if you ask 2-3, and I will give you no, you have nothing before you, and you have 2 on to this side. If you ask 4-7, I will give you 3 no. That's why you discovered you're at the tail. And in general, if you ask 3-8, somewhere in the middle, I will give you 8 and 7. So that's the query model. And this model in some sense capture a fixed point. You only know directions, no global value. It tell you where to go. So that's roughly this model. Okay. And then we basically want to determine what is this randomized complexity. If I give you a head, you find a tail. So that's this problem. Okay.
What's the goal in this problem?
The goal of the problem is I want to establish a lower bound of n to the power d-1 randomized model to solve this. And this will have an implication that fixed point in the query model cannot be found in randomized model in time n to the power query n to the power d-1. Because I already had all the reductions. It's all come to here. I haven't had the reduction to here yet. I just defined this problem right now. Okay. So here is the first step. Clearly, we need to first allow you to build the graph and the coloring, right? So here is a 2 dimensions, actually very beautiful, simple construction, and then I will show you the landscape of high dimension. Then I will give you randomized lower bound for this. Okay. So we define 2 dimension. We define a simple map. If you give me a string, so let me have F map, namely I just duplicate the letter. And so if you give me a string, I duplicate my letter twice. So that's this function. And geometrically, if you give me a string, I want to give you a path. And this path eventually will give you coloring. Okay. So if you give me a string, for example, 1, 5, 3, 7, and I just say, okay, 1 is really corresponding to 1, 1 node, 3 is 3, 3 node, 5 is 5, 5 node, and 7 is 7, 7 node. And when you give me this sequence, 1, 5, which means you want me to walk from 1 to 5, so I will walk this way. I will walk in x direction, and I walk y direction, and I walk x direction. And then you want me to go to 3, I go there. And if you want me to go to 7, I go there. So this will be how the string will give you a path. So that's mapping in 2 dimensions. So let me just quickly argue for you. Intuitively, this already showed that in 2 dimensions, the path problem does not have has a lower bound of n in randomized complexity. Because if I give you random permutation, I ask you to know who is the last element. You have to ask at least n queries. Just think about it. I give you random permutation. You try to tell me who is your last element. You have to ask n queries. So in some sense, this already showed the 2-dimension lower bound. Okay. And so this is how from string you can build a path. Okay. And so the slight tricky part is basically try to argue that when you ask a query here, you can convert into a query into string. So this way you can faithfully using string as a model, and that basically lets me just you just trust me that can be done. Okay. So anytime you want me to know whether you have edge here, I can just ask the corresponding string, then you know whether there's edge to your direction. So let's just trust me this can be done. It's fairly procedure actually. Okay. And so in 3D, in high dimension, let me just give you a 3D case. So here is if I give you 2 non-repeating pattern, and then you want to build coordinate in 3D. So the difference is this map. So actually, eventually, we spend most of the time trying to find a good map. How do you decide you move your string around? And it needs to satisfy certain conditions. In particularly, if I give you any 2, you need to determine A1 and A2. So here you have A1 and A2. I give you any 2 numbers, you actually have to recover the coordinates. So there's certain transformation family you can use, and fortunately, the simple one like this exists. Okay. So here is this 3-dimensional landscape. If I give you a string, and they corresponding to a point using this map in 3D. So I give you 2 numbers go to 3 dimension. In all time, I give you 1 number go to 2 dimension, not 2 numbers to 3 dimension. So then you just define a walk to them. You just do a Hamming correction, namely the coordinate wise you do a correction. So that's what will allow you to do a walk. So this is how you go from string, then you can embed the path. So this path couldn't self-intersect, but it's okay, right? Because we can handle self-intersection paths now. So then you can also argue that because of the property of this map, you can do all the queries locally. Anytime you want to know whether the edge is there, you just need to ask string 1 or twice. Okay. So far I basically just show you all the reductions, and in the next 5 minutes I will close out with the randomized lower bound. Okay. So the lower bound we would like to establish is for string end of string problem, it has n to the power d minus 1 lower bound. So then this reduction, however tedious, will lead you all the way to coloring. Right? So this way we only need to focus upon this non-repeating string and how to produce one. Right? So just like most of the lower bound in randomized case, we call upon Andy's minimax theorem to do expected correspondence. So essentially, we need to, in order to prove a randomized lower bound, we want to fight against every deterministic algorithm with random distribution. So that will give the minimax theorem will give a lower bound. So essentially, I need to produce for you a distribution of non-repeating strings, so that for every deterministic lower bound, it will have a query complexity n to the power d. So then, using my transformation, it will go back to the other model. Okay. So basically, I need to build you this distribution, and somehow complicated enough that you have to really ask so many queries. Okay. So in 1 dimension, I already argued for you. You just use a random permutation of all the letters. Right. So I'm sure you can all quickly argue you have to ask so many questions. But let me just give you a try, and then to set up my high dimension argument in the next 2 slides. So here is intuitive random 1 dimension. You want to know who is the last letter. And so initially your domain has n or basically half n possibilities. Right? You have random permutation. You want to know who is last. Everybody's suspect right now. So then you ask queries. Right? So you go to ask a query of a particular guy, and if you tell you the guy before you or after you, right? So you have a few cases. If your answer is there's no one behind me, then clearly you say, hey, I got my last letter. And that happens with probability 1 over t. Right? That happens with probability 1 over t. So let's assume we do a simple protocol. If you get your answer, I just delete everybody else. So then your set will reduce to a singleton. Right? Because you find it. Right? So, but if you ask query, it gives you 2 letters, someone before you and someone after you. Then all you knew is I'm not the guy. Neither are the one before me. So that's the only thing you know, right? So the only thing you can delete from your search domain is just 2 letters. So that will happen with this probability, and your size will reduce. So it's a kind of this probabilistic, so this is one way to view this, right? It's a probabilistic recurrence. That, the ground saturation, the probability depends on what saturation you have. So if your cardinality is t, 1 over t time you will be successful. The other chance you will lose 2 elements. Okay. So if you solve this recurrence, this random process, right? So you can define this random process. And if you solve this random process, you can easily argue that the chance if expected step, in case step you find it, is basically omega of n. So that you can argue through. So that's one-dimensional case, or two-dimensional Sperner lemma. So this proves two-dimensional Sperner lemma. You have to ask so many questions.
Just a quick question. In the previous figure, why do you remove 11 and 7? Why not 7, 3?
Yeah, I can't remove 7 because I knew 7 is bigger than me. But 7 could be the last one. But I knew 11 is smaller than me. I'm finding the bigger one, right? So I can remove the people before me. Because I want to find who is the last one. Right? So let's just do a two-dimensional one. So then it will give you impression how eventually this thing has to be argued in high dimension. Why we went through certain pain to define string in this particular way. Okay? If we have 2 repeating string, so here is how it's constructed. I randomly permute the even number to put on the root. Okay? And so then I build the other half. I build a random permutation. For each of the element, I build a random permutation of the odd numbers. Right? So in some sense, you're doing this dimensional reduction. Right? You keep on messing up your dimension. So this is one slightly clean way to do it. Okay? And but the important thing for fixed point, which we're so far from there, so I have to just point out a few things. I need to get 2 in the front for technicality. I need to make sure those letters are connected. So there's only a few minor conditions I need to give to you. Right? So I have agreement where to leave, where otherwise your path will not be conformal. So just take it that's a condition I need to put in. And then here is how I build my string. So for each of this guy, I build a 2 non-repeating string. So I just insert my 8 everywhere, my 6 everywhere, and my 4 everywhere. And then I just append them as a bigger string. So this is a string ultimately given to you to query. And I will argue that for this string...
Sorry, I'm kind of tired. So it's 2 non-repeating?
It's 2 non-repeating because of it even only appeared this way. Yeah, so clearly it's 2 non-repeating. So that's why we have even separate odd to make it 2 non. Otherwise, it's slightly harder to argue. So that's.
What are you going to? So for 2 non-repeating, that's fine. But are you ever going to deal with D non?
Yeah. So then you just recursively build this thing. That's why it's a multiple layer to build such a thing, right? And so this type of problem is very interesting. Once you figure out the 2, then the same proof will go through. But 1 and 2 are so different. You have to argue very differently because there's the significance difference here. So here is basic analysis. Eventually we have to write down a recurrence, probabilistic recurrence. That is, your old search space is, you know nothing initially. Then gradually you're losing locally. Okay, I'm not the last one. Because if you look at this string, essentially all you're interested in to find the last one. And in every bucket, actually you don't care anything. You only want to find the last one. Right? Because you just want to find where I enter, where I leave. All the intermiddle ones are transient. And finding them does not help you that much. You can only get your string shorter a little bit. But if you accidentally query this guy, then you can kick everybody out. You win right away. Right? So there's a few informations are more important than some other informations. So this is sort of randomized model. Few queries is more important, and then we have to ask what's probability may be discovered. And so essentially you have this space of how much you know already. Namely, those are still the possibility to be the last one in their own respective domain. And globally, you have the union of those. You know who is particularly still the last one. And so if we want to prove, for example, in 2D, this is n squared. In d dimension, eventually it will be n to the d. Okay. And so if you ask for query, for example, if you happen to be the last one, this will happen with the union of probability, right? You have to outguess everything to get the correct one. So this happens with 1 over t probability. And otherwise, if you get some other for other number to know, and you only knew something about this smaller pocket, and they will happen with their own probability, it will go to 1. Okay, so there's different layers, right? So you get different layer information with different layer of probabilities, right? Depending on where your query suddenly hit. And so essentially, you can write down, you can go down this to have you can go down this with a recurrence, saying that ultimately you can get the answer with this probability, and at each layer you have probability to reduce their size with their probability. Otherwise, you only lose 2 elements, because you only know who is before you, who is after you. Right. So this is the statistical model recurrence you build, and essentially we clearly prove that this actually is n squared. In general, is n to the power d minus 1 d. So that's basically the whole proof, the tedious part. So since I have 1 minute, so let me conclude. In d dimension, basically you build a d-dimensional tree like this. That's a d-dimensional tree, and you have this complexity. But all the argument is the same. You can regulate the argument in the same way. So I think one of the beautiful conjecture is the following. If PPAD is in P, then maybe PLS is in P. I knew there's an oracle which separated them, but who believe those oracle results? Right. So that's this talk. Thanks. Yeah.